Welcome to Google Cloud AI Developer Relations Virtual Training. My name is Andrew Froelich, and I'm a staff member at Google Cloud AI Developer Relations. This is part 2 in our Junior Data Scientist training. Today, we're going to talk about the design patterns in wide convolutional neural networks. So let's give you some background. Early on, when convolutional neural networks were being designed, they were trying to go deeper and deeper and deeper into layers. And of course, as we've explained before, or you might know yourself, as they went deeper in those early years, they had problems with things like vanishing gradient and exploding gradients. To some degree, those were being addressed by residual links and by batch normalization. But in parallel, at the same time, other researchers experimented with the concept of going wide. And what they mean by that is instead of having sequential convolutions going deep, what about if we have parallel convolutions and then concatenate their outputs together? So one of really the very first state-of-the-art ones to experiment with wide convolution layers was the Inception series, V1, which was the winner of the 2014 ImageNet contest, also known as Google LeanNet, introduced the concept of an Inception module. So the Inception module is a convolution layer with parallel convolutions of different sizes, with the outputs from each convolution are concatenated together. So the principle they proposed in their paper was instead of trying to pick the best filter size for a layer, have each layer try different filter sizes in parallel and let the layer learn which size is best. So this is what they called the naive inception module. This is what they first experimented with before they went to the contest. And as you can see here, is they take their input and they run it in parallel through 4 different convolutional layers: a pooling layer, a 1x1 layer, a 3x3, a 5x5. You can see these are different filter sizes. Then they take their outputs and they concatenate all 4 outputs together. So let's go ahead and just write a naive inception module. It's really simple. We're going to assume X is our input. So we're going to create these 4 convolutional layers: our max pooling layer, our 1x1 layer, our 3x3 layer, our 5x5 layer. All of them take the inputs. We'll just call the outputs X1, X2, X3, X4. And then we're just going to concatenate them together. Okay, so you might have noticed that on all of these, we set padding equal the same. And we did that because we want to make sure the height and width dimensions of the input are preserved. We're going to concatenate all these feature map outputs together. And for the concatenation operation to work, they need to be the same size. So if we took that little bit of code and we did a summary on it, and assuming that the input to the layer was 28 by 28 with 256 feature maps, we would see something like this. Our pooling layer would come out exactly the same: 28, 28, 256. Our 1x1 had 64 feature maps. You see it there. Our 3x3 had 96. Our 5x5 had 48. After the concatenation, we would add all these together, and we're going to have 464 feature maps. Now, if we did a summary for a naive inception module and looked at the number of parameters, we have 454,000 parameters to train just for one inception module. That's like 500,000. That's pretty big. So in V1, they went a little step further, and they wanted to reduce the complexity of that module. So they did what we call factorization. That is, how can you refactor a pattern into a less complex pattern, but maintain representational equivalence. That is, the information coming out from the refactored one is as representative, has the same representative power as the previous one. And the design they came up with, they referred to as the bottleneck convolution. And what they did is they added a one-by-one bottleneck convolution to all four, to the one, excuse me, to the pooling 3x3 and 5x5 branches. And this reduced the complexity by nearly 2/3. Yet in their ablation study, they got just as accurate results. Now, you may also ask, what can a 1 pixel size filter being scanned across each channel learn any feature? And if you were in earlier training or familiar with it, that's not its purpose. Its purpose is to either expand the number of channels or reduce the number of channels, or in other words, feature maps. And when it's being used to expand, we refer to it as a linear projection. And when we refer to it as being to reduce, we refer to it as a bottleneck. So let's go ahead and pictorially look at this. Okay, so here you can see we've added this one by ones to those three branches. And just to repeat here, when it's a linear projection or expanding, that's kind of analogous to learning the optimal method to upsample your data. And when it's a one-by-one bottleneck, reducing, that's analogous to learning the optimal method to downsample. So let's go ahead and write that Inception V1 module that was used in the 2014 ImageNet contest. So X here is our input. So as you can see in our max pooling layer, we take the input, we run it through the max pooling, we take that output as input to our one by one. Then let's look at the second layer. It was already a one by one, so we didn't add another one by one, just leave it as is. Then we look at the next layer. This is our 3x3 one. So our input goes through the one by one bottleneck convolution, then the 3x3. And we see the same thing on the 5x5. The input goes into the one by one convolution, its output goes into the 5x5. So our four branches, X1, X2, X3, X4, we just concatenate them together. Now, if we did a summary on this module, we would find that we only have 198K parameters to train, which is substantially less than the 544 version in the naive Inception module. So let's go look at the overall architecture of the V1. Many of you have seen that original picture that they published that had all those little blocks and all those little branches, and it was really, really long and really difficult to grasp. But here what we've done is we've retrofitted that architecture into the idiomatic procedural design pattern, which makes it much easier to comprehend. So it contains a stem convolution. There is a learner where we're going to do the feature learning, a classifier where we're going to do the classification learning. Within the learner, we have inception groups that have one or more inception blocks. Additionally, we have this thing called auxiliary classifiers, which we'll discuss here in a few moments. Oh, actually, we discuss it now. Okay. The Google LeanNet architecture introduced the concept of an auxiliary classifier. Now, the principle here is that as you went deeper into neural networks, that is, as the front layers got further and further away from the final classification layers, the front layer, that back, final classifier contributed less to the front layers in updating it. And so those layers were more exposed to the vanishing gradient. Okay. And so what they thought is by placing additional, say, helper classifiers sort of in the middle of the architecture, that being closer to those front layers, they would help train those front layers in addition to the final classifier and eliminate or reduce the vanishing gradient. This is just a picture of their auxiliary classifier in V1 and in V2. It did seem kind of overly complex. I'm not going to go into the detail other than to point out in their classifiers in the Inception V1 architecture, they use dropout for regularization. The classifier for the Inception V1 is more of what we traditionally thought of. You had an average pooling layer, which reduced all the feature maps to 1x1s, where of course that 1 pixel value is the average of all the values of a final feature map. It's then flattened into a 1D vector, followed by dropout for your regularization, and then finally the classifier. So Inception V2 introduced their concept of factorization of more expensive convolutions in the Inception module to less expensive ones to reduce computational complexity. And again, the concept of representational equivalence, that is, reduce information loss from what they said was representational bottlenecks, yet retain the same representational power. Now, as they observed, the larger a filter size is in the kernel, the more computationally expensive it is. So take, for example, a 5x5 convolution. Now that's going to have 25 pixels or 25 elements that you're going to be using when you do a dot product matrix operation, or what's sometimes just called a map mall. Compare that to a 3x3, which is going to be 9. That makes the 5x5 2.78 times more computationally expensive than a 3x3. So in the Inception V2 module, they experimented with replacing a 5x5 by a stack of 2 3x3s. Now that resulted in a 33% reduction in the number of parameters. And in their ablation study, they found that it got as accurate as the 5x5. So it had representational equivalence. So let's just take a quick look at what that block would look like. Okay, so here is they took that 5x5 and they changed it into a stack of 2 3x3s. And as noted actually in the study, the overall accuracy of the V2 architecture actually increased over V1. So let's just go quickly write that. There was also another thing in V1, they hadn't yet taken, they didn't really have the knowledge yet of batch normalization, but by V2 they did. So they added batch normalization into their layers. As you can see, after each convolution, we have our batch norm. There's our batch norm. The style used here was, you do your convolution, then the batch norm, then your activation function. And today, that convention, we sort of donate with this terminology here. We call it conv, batch norm, ReLU. So you'll start seeing this more and more in my presentations, as well as in papers and literature. Now, if we took a summary on the V2 module, we see we're down now to 169,000 parameters compared to the 198,000 in the V1. So let's leap ahead to V3. So V3 introduced really a new design to the macro architecture, as well as redesigning the stem group and reducing to a single auxiliary classifier. Now, a couple things I'm going to point out. I'm not going to spend too much time on V3 because it really comes complex in design. And two things after the Inception series. Nobody ever again went to this level of complexity in the design. And the concept of auxiliary classifiers fade away. They didn't really prove out to do what the authors thought they would do. But here, what we do now is in V1 and V2, all your groups and the corresponding blocks use the same type of Inception module. Well, in V3, they changed it. So group 1 uses the original Inception modules. Group 2 uses a different type of Inception modules. And group 3 used a yet a even different type of Inception module. And between them, they introduced a new concept called grid reduction, which were these modules that reduce the size of the feature map. So, of course, going through here, my feature maps, I'm increasing the number of feature maps, and then I reduce their size. I go here, I'm increasing the number of feature maps, I reduce their size, and then I go through the final group C, and then when we get in the classifier, we're going to do that aggressive downsampling through global average pooling and then flatten it into a 1D vector before we go into the dense layer. So again, I'm going to be very quick. So if you look at the V3 blocks in the second group and block 2 and C, you can see they are very different. They're also using, notice these, like here would have, they've replaced things like a 7x7 with a 1x7 and 7x1. Or a 3x3 is replaced by a 1x3 and a 3x1. Those are called separable spatial convolutions, which is another way of reducing the complexity of a convolution. So these are the grid blocks. Again, I just kind of show you the picture that they are very different. You can see how in the 3x3s here, here's our stack of 2 3x3s that replaces a 5x5, but you can see the final 3x3s are strided, meaning it's a strided do. They're doing feature pooling for your aggressive reduction. So let's kind of work our way to what a separately spatial convolution is. So let's look at a normal convolution. So look at it from, let's start with the input. So we got an RGB image. It's got 3 channels, red, green, blue. We have a kernel or our filter. This is a 3x3 example. We're going to slide it across the image. Well, we don't do it one layer at a time or one channel at a time. It's actually deep. So when I'm doing my map mall operation, I do it across all 3 channels at the same time, producing a single feature map. So whatever value I get here across deep-wise map mall is what I put here. So this is when I have a single filter. Now, if I have a lot of filters like 256, it's the same thing, but I'm going to come up with 256 of these feature maps, one for each filter. Now, in a spatial separable convolution, the idea is to break a convolution, or what they call a 2D convolution, like a 3x3, into 2 smaller 1D convolutions. So we can take something like we say a convolution as a height by width, and then factor it into a height by 1 and 1 by width. Okay, so and when we do this, it lowers the total number of computations by 1/3. So think of this as the normal convolution here that goes deep, right? And we're going to replace it now with a height by 1. So in our case of, let's say, a 3x3, this is a 3x1, and that's going to be applied deep. And then we're going to take that and run it through a 1x3 and go deep. So here's a little bit of the math here, and I won't go into detail, but had we used a 3x3, okay, that of course would have given across 3 channels RGB, we would have had 27 multiply operations, 27 map mul operations every time we move that filter. Okay, when we factorize it like this, we end up having 18 multiply operations. So there's that reduction that we're talking about. The stem, they also made overly complex. You'll never see a stem this complex again. So here you can see One of the things they did is they were still using in V1, V2 an extremely coarse filter, a 7x7, which nobody does anymore. But the theory they had of replacing a 5x5 by two 3x3s for less computational complexity and the same representational equivalence, they theorized that you could take a stack of three 3x3s to replace a 7x7, reduce the computational complexity, and have the same representational equivalence. That's what they've done here. Okay. And then they did some downsampling here with a bottleneck convolution, further aggressively reducing it with another strided convolution, and continued to reduce the size of the feature maps with a max pooling. They simplified the auxiliary classifier. Now it looked like a regular classifier. You just had your average pooling. We're not quite. You still have this convolution in the middle using a 5x5, then flatten it and go through a final dense layer. So the next really important state-of-the-art architecture that went with the concept of a wide convolution is ResNext by Microsoft Research. And that was the first runner-up in the 2016 contest, and introduced the idea of a wide residual block. Okay, and this concept of cardinality, which is really just another term of for width. And in the architecture, they introduced this idea of a convolution. I did a split, branch, and merge method of parallel convolutional blocks. So let's go ahead and take a look at what I mean by this. So if you remember in a ResNet, okay, they used the idea of a bottleneck convolution, or I mean a bottleneck residual block. That means it had a 1x1 bottleneck convolution to do dimensionality reduction. It had a 3x3 convolution where you did the feature extraction and feature learning, followed by a 1x1 linear projection convolution to expand the number of filters. Okay, here what's different is we replaced the 3x3 regular convolution by what they called a group convolution. And in a group convolution, we're going to actually take all those feature maps and we're going to split them into groups. Okay, and each group is going to separately go through a convolution, and then their outputs are going to be all concatenated together. And again, like a residual block, in the end, the input is going to be added to the output. So let's look at that operation, that group convolution operation, which they referred to as split, transform, merge. Okay, so we're going to have our input, which are all those feature maps, and then we're going to determine a size, a group size. So let's say we have 128 feature maps coming in, and our size or our cardinality is 32. Well, that would be 4 groups of 32. The first 32 feature maps, the next 32 feature maps, and so forth and so forth. So we would have 4 groups, and each group would separately go through a 3x3 convolution, and then the outputs of all those groups would get concatenated together. So this is your split operation. This is your transform operation. This is your merge operation. So here we write some code demonstrating that. We'll just start with the outer part. So here's your 1x1 for the dimensionality reduction at the beginning. Here at the output is the 1x1 for your dimensionality restoration. Here's our identity link of adding the input to the output. And then in between is our group convolution. And this is just kind of their terminology using cardinality, but really you could say partition or width. So we want to figure out how many filters per partition in the group. Okay, and these are, of course, our groups. And we're going to go through based on the cardinality. So let's say it was 34 and break it into that many groups. Okay. And I won't go into the syntax here of a lambda and slicing. That's very Pythonic. Okay, but effectively what I'm doing is I'm splitting up all the feature maps into the number of groups specified by the cardinality. Each one is going to run through a convolution, okay, separately. I'm going to remember them. That's what this append is about. Okay, and then I'm going to concatenate the outputs from all those group convolutions and back into one feature map. So in ResNext, let's look at the learner. Now we're going to skip past the stem. It was a conventional stem using a very, coarse convolution, a 7x7 followed by max pooling. But in there, it is the learner consists of 4 groups of ResNet groups. Okay, and of course, each one of them has, one or more blocks into it. Now, there is a slight different change here. Okay, in ResNet, if you remember, because we doubled the number of filters, and we still do across groups, and ResNext, they still do the same thing. The way they handled it is they always made the first residual block sort of that special case where it did a linear projection. They removed that idea in the ResNext. All the residual blocks are identical. And instead, in between, they put a strided convolution to double the number of filters coming out of a group here to match the input of the next group, which is going to start with twice the number of filters. Okay, so the another one around the same time was known as the Wide Residual Network, or WRM. It came out in 2016 from researchers at the Paris Tech University. Now, the authors in this one theorized that as you went deeper in layers, feature reuse is diminished and it takes longer to train. Now, if you recall, in a residual link, we're attempting to reuse some of the features through the link, but because we do an add operation, we kind of dilute it. And so as we go deeper and deeper, even though we're remembering some of the input, it's more and more diluting. And so their theory is the more wide you went on a layer, the more feature reuse you would have. Okay, and that you could decrease the depth of the neural network and get the same accuracy, and therefore being more and more immune to things like vanishing gradient and exploding gradients. And what they found in their paper and ablation study is they created a wide residual network with just 16 layers that could outperform other state-of-the-art architectures at the time. So if we look at sort of a big overall view of this, okay, we have our STEM group, we have a learner and a classifier, and the learner is going to consist of multiple wide residual groups. Another thing they did in a WRN is they borrowed this idea, or continued with an idea from the ResNet V2, of changing the order of batch normalization to a pre-activation batch normalization, which in the ResNet V2 study showed that it outperformed the older post-activation. And we refer to that as terminology BNRE convolution, that is batch norm ReLU convolution. And as in the ResNet 34, it used 2 3x3 convolutions instead of the bottleneck style. And the author stated that the bottleneck design was not needed due to it, the bottleneck was designed to handle networks going very deep. In this case, because the network wasn't going that deep, they used a slightly more computational expensive one, but they felt it encouraged more feature reuse along the wide layer. And they did this thing of instead of doing dropout at the very end, that is the top layer, of actually putting it in between each convolution. So if we look at the picture of here, you can see that has similarity to other residual blocks, but a little different. It's got the two 3x3 convolutions, but now the width factor here, K, that's what they call it, controls how wide those convolutions were. And in between each convolution is now a dropout. Again, just a little quick code snippet here. You can see the first 3x3 convolution. You can see the next convolution here. Okay, and you can see that between the ReLU, and this is what they said, you put the dropout between the ReLU and the second convolution, and there is their dropout. Okay, well, that's the end of that particular training thing. We have a lab that goes with this. You can find it here by going to this bit.ly link. And again, thank you for attending our virtual training.